Okay, quick review. Diffusion's the easy one, right? Osmosis is where it gets weird. And I think most of you are pretty much on board now with how the water moves and why it moves, sort of. What we haven't really talked about is how hard it is to remember the difference between hypertonic and hypotonic. They are so similar. And you know I'm all about dumb ways to remember stuff, or maybe you don't, but now you do. And so here's how, I mean, these are seriously two terms that I've gotten confused my whole life since I learned them. The way I finally now remember it is this. My 12-year-old brain goes, okay, the difference between those two words is that, right? And so that right there, pee. It's like the cell has to pee. It's losing water, right? Hey, your 12-year-old brain is great for remembering stuff. So that's how I remember it to this day. If that works for you, use it. If it doesn't, find something else. But they are a pain in the butt to keep straight. So hypertonic loses water. Hypotonic gains water. I had somebody say that O makes them think of a swelled up cell. Maybe that helps. Whatever. But you're going to have to remember it. And today that will come into play with the beaker problems that you've got. Okay. Moving on. The great question that a couple of you have asked is, okay, Sandro, if stuff is stuck in the cell, can't cross the membrane, how did it get in there? Why is it there in the first place? And the answer is you need stuff that won't go easily through the membrane all the time, right? You got to get glucose in there. Various proteins have to come in. Amanda?
Made inside the cell.
Say it again? Some things are certainly made inside the cell. You're absolutely right. And they don't ever leave. But some things do, even things that are too big to cross the membrane by diffusion. And so we're going to answer that question in a couple of ways today. The first is active transport. Active transport is a way of getting stuff in or out of a cell, spending energy. You have to use energy. You can move things against the laws of diffusion. In other words, you can make things go from low to high concentration with active transport. That's why it costs energy. Couple examples here. One you have seen already. We call it bulk transport. But the two kinds are endocytosis and exocytosis. This is exocytosis. Remember, we use that word vesicle a lot. When you're sending something out of the cell, you know, from the Golgi via a secretory vesicle, and you fuse that vesicle with the cell membrane, and basically the cell just kind of spits out the stuff it needs to get rid of. That's exocytosis. Endocytosis, I drew on the board for you, remember? In the endosymbiotic theory, endocytosis is the way that cell eats, right? It's the way an amoeba also eats. It bends its cell membrane using its microfilaments and pinches off that membrane on the inside of it. That's endocytosis. Both of those cost energy. Both of them obviously can get something bigger than would normally cross into or out of the cell. Does that make sense? Any questions? So that's kind of the quick and dirty way of doing it. Just spit it or swallow it. Write that down. That's also how some white blood cells kill stuff. They endocytose it and then use a lysosome to blow it up. This more finely controlled active transport example I'm going to give you is called the sodium-potassium pump. It's not the only pump mechanism in your cells, but it's certainly the most common. You have multiple sodium-potassium pumps in pretty much every cell in your body. Hopefully you're aware that Na and K are the periodic table symbols for the elements sodium and potassium. Notice the positive sign next to both of them. We are talking about sodium and potassium ions, charged versions that have lost electrons. This is still active transport, so it requires energy. And the basic mechanism is when one rotation of the pump is over, 3 sodiums have been pumped out of the cell, 2 potassiums have been pumped in. Three consequences of that thing running basically all day long, 24/7 in each of your cells. 2 of them are easy. What is pumping a bunch of sodium out and a bunch of potassium in all day going to cause as far as concentrations? What's there going to be a lot of inside the cell? There's going to be a lot of potassium inside. There's going to be a lot of sodium outside. Those are the easy ones. But then there's the consequence that comes from constantly pumping 3 positive things out, but only 2 positive things back in. What's that going to do, Dominic?
It's going to make the cell negative.
It's going to make the inside of the cell slightly negative. The inside of all of your cells are slightly negatively charged. And that turns out to be absolutely essential for all of your nerve and muscle cells, which all work on an electrical charge mechanism that doesn't exist unless you've got that slight negativeness in your cells. The nerve impulse or muscle contraction impulse is basically a brief depolarization, a brief coming back to the positive charge that runs all the way along the length of the cell. You want to understand that stuff, it's the coolest stuff. Take physiology next year or the year after if you want to get into nerve and muscle stuff. It's my favorite stuff to teach when I teach it. So yeah, you can see it working here. The 3 sodiums fitting into one side of the pump. The pump using, this is the energy part. We'll talk about what that is next chapter. Opening out to the outside of the cell, letting the sodiums out, and then it's got the 2 slots for the potassiums to slide in. Energy molecule comes off, and in comes the potassium. Sorry, it's a little jerky, but so those are your 2 examples of active transport. Really 3, I guess, if you include endo and exocytosis. The alternative, if you want to get something big into or out of a cell, if you don't want to spend energy, we have what's called facilitated diffusion, a type of passive transport. This is where those transport proteins you remember from the beginning of the chapter, specifically channel proteins, which was the picture we showed you, facilitated diffusion. By the way, what does facilitated mean? If I facilitate something, what am I doing, Iowa? Controlling it? Not quite. If I facilitate a meeting, if I'm the facilitator for that meeting, what am I doing? Might be the host. Basically, I'm there to help make sure the meeting goes well, right? I'm there to help. That's what facilitate means. It means to help. And so this is just diffusion with a little help. And the help comes in the form of a hole in the cell membrane. But a hole that's very specific and only allows a certain type of molecule through. You don't have to have any energy for this one, except for the energy that it took to make the channel protein. Again, they tend to be very specific. The glucose channel in most cells is an example that would be good to remember. It is important to remember that this is diffusion. Diffusion with help, but still just diffusion. So you can't just force something across those channels, it's still going to have to be high to low concentration. You want the glucose to go in through the glucose channel, and you got to put a higher concentration outside the cell than there is inside the cell. And a reminder of the diagram we used before, and that was our example of a channel protein. Flip back real quick to fluid mosaic model stuff, where we talked about the 3 kinds of proteins. I have stuff about them here on this next slide. I'm not sure how much is the same or different, so I'm just going to let you decide what to add. But just to kind of refamiliarize you with these membrane proteins, there were receptor proteins. Remember, they cause changes in a cell when specific molecules bind to them. Insulin receptors are basically receptor proteins that when insulin fits into them, they let glucose into the cell. They open the glucose channels, right? Sense of smell was the example we used at the beginning. So this might just be the examples that are new. If you want to add those there, that's fine. If you want to add them at the end, that's fine too. Transport proteins, remember, allow stuff across in both active transport, like the sodium-potassium pump, facilitated diffusion, the channel protein, right? Both of those things would be examples of. And finally, the marker proteins, which allows cells to recognize other cells, particularly important to the immune system. And it's usually, remember, carbohydrate chains that are hanging off of those marker proteins that serve as the ID tags. All right, eggs next. I'll walk you through what to do. Today is, really kind of the same procedure as yesterday, except for one thing. And that thing is that corn syrup is gross. And it gets everywhere. And when it hardens, it turns into like this fossilized, semi-sticky stuff that I can't scrape off the sink. So I want you to be very careful and cognizant of cleaning up after yourself today. Whether it's you get it on the scale or on the counter. I would definitely recommend having warm water running in the sink while you dump out your corn syrup, because that's what you're going to do. You're going to dump it through your fingers, dump the egg into your hand again. You're going to have to rinse for a while to get all the sticky gunk off of you and the egg in the cup. But once you do, put it back in there. Solution 2 is distilled water. Who can tell me what distilled water is? Or how you distill water?
Isn't it like you boil it and then condensate it back into it, boil it again over and over again?
The simplest setup is just a boiling pot and a receiving pot and a piece of metal tilted towards the receiving pot above the boiling pot and the receiving pot both, so that when the steam condenses on the metal, it drips down the metal and drips into the condensing pot. It's a way to boil water off of all of the solutes that are in it so that you get very, very, very pure water. It's about the purest water you can get cheaply, okay? And so distilled water is the purest water we can afford. You're basically taking an egg now that has all kinds of like solutes and stuff inside it and putting it into the purest water you can. Again, it's a bigger problem. Again, it should be a fairly easy one if you've been keeping up. Put your predictions and your measurements. This is going to be the number you'll take from the scale will go 2 places. It'll go in egg mass after immersion in solution 1. That'll be the same number as egg mass before immersion in solution 2. Make your hypothesis about what's going to happen, and then I'll fill you up with the distilled water when you're ready. And yeah, Sam. I think that's probably a good idea. Yeah. Remote people, feel free, if you don't have distilled water, you can use tap water. It'll be okay. It might not be quite as dramatic. So either way. All right.